Hi everyone, I'm Ahalya Prabhakar from Northwestern University, and I'm going to talk to you about our work in swarm control titled Ergodic Specifications for Flexible Swarm Control, from User Commands to Persistent Adaptation. So the question we were interested in answering is, for an operator with a robotic swarm trying to accomplish a dynamic time-sensitive task, how can we specify a swarm controller such that the operator can both manage the swarm and have the swarm manage itself so they most effectively accomplish the task? To do this, we want a swarm control formulation that is amenable to self-managed control, so the operator does not have to constantly monitor and direct the swarm or the individual agents in it, and also have the swarm be able to dynamically take in and adjust their behavior in response to both user commands and environmental information that can inform task completion. In this work, we focus on the scenario posed for the DARPA Offset Urban Swarm Challenge, where there is a swarm of robots tasked with exploring an unknown environment to locate and secure Easter eggs in the environment. In addition, there are adversarial or disabling devices located in the field that when a robot spends too much time near it, the robot gets disabled. Finally, the swarm should be able to take in and adjust their behavior to an operator's inputs for how to accomplish the task. Our contributions in this work are to develop a swarm control formulation for solving this joint operator swarm task. To do this, we demonstrate the use of ergodic specifications for specifying task goals and user commands and defining task allocation as spatial distributions for high-level planning. We also develop a full swarm control formulation using decentralized ergodic control that is amenable to both user-based and self-managed swarm control and is dynamically responsive to environment updates. Furthermore, we designed the full end-to-end pipeline for this control formulation from a tablet interface we developed for user commands to onboard control of robotic agents. We demonstrated in both a virtual reality simulated test environment for a swarm of quadcopters assisting an operator in the field and on hardware in real-world experiments at the DARPA offset field tests using a swarm of Aeon rovers. So how does the swarm control formulation actually work? We use the idea of ergodic specifications in order to generate swarm behavior. Ergodicity states that the amount of time a robot spends sampling in a region in the workspace is proportional to the spatial statistics of the region. To that end, we can compare the spatial statistics of the time average trajectory to a target spatial distribution using Fourier decompositions. We define the ergodic metric as the weighted difference between them. For a swarm, we can use the spatial statistics of the collective swarm trajectories and compare them to the target spatial distribution to generate individual swarm control that minimizes the ergodic metric. For experiments, we use the ergodic control formulation as a planner wrapped around an RT star and obstacle avoidance algorithms instead of directly as a controller in order to generate the appropriate swarm behavior. But given this formulation, how do we generate the target spatial distribution that guides the swarm behavior? We can generate target distributions that reflect the evolving task behavior. For initial exploration over the workspace, we specify a uniform distribution that reflects the importance of exploration over the workspace equally. We can also generate adaptive distributions reflecting environmental stimuli. If an Easter egg is located by an agent, the location is communicated to the swarm and they update their distribution with a Gaussian peak at the Easter egg location, such that the swarm naturally congregates and secures it. If a disabling device is located, they update their distribution with an inverse Gaussian peak at the device location, such that the swarm naturally avoids it during exploration. What's great about this as a way of specifying swarm behavior is that these distributions are additive, so that they can be combined to accommodate multiple task objectives at once. Here, the swarm is simultaneously avoiding a disabling device and, when an Easter egg is located, converging on it. We can also generate distributions for user input. An operator can shade in regions of interest over the workspace, here it is a bimodal distribution, and the swarm updates their distribution to explore with respect to it. We developed a tactile tablet interface for the user to communicate their needs to the swarm through this shading mechanism. Here we see exploration of a similar bimodal distribution communicated through the user interface in the VR simulator, and on the swarm hardware at the field tests. We see this swarm exploring with respect to the operator's needs without the operator needing to adjust their commands based on the number of agents in the swarm, nor commanding each agent individually. Overall, this work presents a novel formulation for swarm control that is dynamically adaptive to environmental information and can accommodate a user's inputs. For more information, media, and access to code, feel free to visit the paper's website page shown here.